So the two parameters of relative motion we've seen so far, one is relative position, where we've understood the formula that position of one object B with respect to another frame A, or with respect to another moving object A, is given by the absolute position of B in the ground frame minus the position of A in the ground frame. And then the next one we saw was relative displacement. So suppose with respect to ground frame, in a certain interval of time, A and B make certain displacements. Then relative to each other, in A's frame, for example, B's displacement becomes displacement of B minus displacement of A. So these are the two parameters that we've seen so far. Okay. So now today, let's start with the next parameter, which is relative velocity. So this is, for example, the relative velocity of some moving object, let's say B, with respect to another moving object A. So how it will be defined? It is the rate of change of the relative position or displacement of with respect to E. So the definition of this quantity becomes that this equals to instantaneous rate of change or differentiation with respect to time of either the relative position or the relative displacement. Now, if you apply the above definition, you can see this therefore becomes equal to rate of change of difference of positions or difference of displacements, SB minus SA, the ground frame. So further expanding this, this becomes instantaneous rate of change of B's position minus instantaneous rate of change of A's position in ground frame. Or if we are going by the second definition, we can apply it and say it is rate of change of SB minus rate of change of SA, which is A's displacement. Okay. So next thing you can see here that this is nothing but velocity of B in the ground frame, and there is nothing but velocity of A in the ground frame. Same here also. This quantity, okay, this rate of change is nothing but velocity of B, velocity of A. So like that, this becomes this. So instantaneous relative velocity of B with respect to A. The definition follows the same pattern as you can see above for relative position and displacement. The relative velocity is the difference of the absolute velocities, or the velocities in the ground frame. That is why, for example, you can see that if you have that situation of two objects moving parallelly, suppose this is moving at 10 and this is moving at 15. You can see that in one dimensional system, we can write these as plus 10 and plus 15 in meters per second. So velocity of B with respect to A will become plus 5, whereas velocity of A with respect to B will become minus 5. From the frame of B, the object A will look like it's going backwards. Whereas if we have another example where two objects are moving towards each other, so with proper sign convention, this will be written as plus 10, be written as minus 5. So velocity of B with respect to A here will become minus 15 when we apply that definition, and velocity of A with respect to B will become plus 15. So just make a note of this definition of relative velocity with these examples. We'll continue with some more.
So what does the minus sign here indicates?
Okay, so hope these are clear. Now let's look at another example of relative velocity. So we have this situation where rain is falling vertically. With a vertical velocity vector like this. Suppose it's like this, okay. But there is a vehicle that is moving horizontally. At a velocity like this. So rain droplets are falling vertically at a velocity, let us say 36 kilometers per hour. And the car moves horizontally at a velocity of 27 kilometers per hour. Find the velocity of the rain relative to the car. An observer with the car will see plane to be slanted with respect to the vertical. To find the velocity of the rain relative to the car. Okay. And its slant angle with respect to the vertical.
Sir,
Yes.
sir, slanted with respect to what?
With respect to the vertical. Yes, Siddharth, that is correct. The answer that you sent is in meters per second, right? Yes, Akshat, your answer is also correct. And the angle is correct, Siddharth. Okay. So here what we will see is that, yes, in meters per second, it will be 12.5. Okay. Basically, it's vector algebra. You can see that the velocity of the falling rain is vertically downwards, and it is 36 kilometers per hour, or that is the same thing as 10 meters per second. Whereas the velocity of the moving person, represent that as a vector, it's horizontal like this. It's perpendicular to this, and that was 27 meters per second. Okay. Or 7.5 meters, sorry, 27 kilometers per hour. Or 7.5 meters per second. Yes, very good. That's correct. So now the relative velocity of the rain with respect to the man, that will become this vector, because that is the vector difference of these two. And the angle at which it is slanted to the vertical, that's this angle, let's say. That's the same as this angle here. So you can see that now these two are perpendicular to each other. So the magnitude of that velocity will become and it is slanted at okay. So this is the example of application of relative velocity concept in a two-dimensional situation. Okay, so now let's move on to the next and final definition of parameters in relative motion. So relative acceleration. So relative acceleration will be defined as the rate of change of relative velocity with respect to time. Further, you can see we can express the relative velocity of B with respect to A as the difference of their velocities in ground frame. And then on operating the rate of change, this becomes rate of change of VB minus rate of change of VA. So this becomes acceleration of B minus acceleration of A. Okay, so let's understand a couple of examples with this. Okay. Now, one of the things we'll also realize on the way is that relative acceleration gives you a basis for understanding the logic behind pseudo force, the concept that you would have seen in Newton's laws of motion. When you apply Newton's laws to an object or to a free body in a non-inertial reference frame, in other words, an accelerated reference frame, the reason why you have to include the pseudo force is basically to do with to compensate for the relative acceleration uh, principle. Okay, so anyhow, let's discuss with an example first. So we have this situation. Let's say there's an elevator which is accelerating upwards at a uniform rate of 2 meters per second square. Okay. And it's a freight elevator, so the height is pretty large. It's got a height of 6 meters. Now, a bolt comes off the ceiling of the elevator and falls to the floor. So let's say it comes off the ceiling of the floor, sorry, of the elevator at t equal to 0 and hits the floor at time t equal to t. Take acceleration due to gravity as 10 meters per second square. First of all, what is the acceleration of the bolt relative to the elevator's frame? And find this time t. And third part, if the elevator started from rest at t equal to 0, then find the displacement of the bolt and elevator from t equal to 0 to t equal to 0. So the elevator has a uniform vertical acceleration equal to 2 meters per second square, as you can see, and the height from ceiling to floor inside is 6 meters. Okay, so just try this out. Yes, very good, Vineet. That's correct. Siddharth, your answer is also correct for both acceleration and time. Yes, Soham, it's correct. Only it's in meters per second square, right? Okay. So what we can see here is for the first part, if we take a one-dimensional system, the acceleration of the elevator we can write as plus 2 meters per second square because it's upwards. The acceleration of the bolt is minus g or minus 10 meters per second square downwards. Because in ground frame, the bolt is in free fall. So the acceleration of the bolt with respect to the elevator, as a vector equation, it is like this. So here with sign convention, it will become minus 12 meters per second square. Or you can say that the acceleration of the bolt with respect to the elevator is 12 meters per second square downwards. Okay, very good, Siddharth. That's also correct. So now what is happening is that what the person inside the elevator is observing is that the bolt starts from here at t equal to 0 with initial velocity equal to 0, but with an acceleration of 12 meters per second square. And at some time t, it hits the floor after having completed a displacement of 6 meters. So in the elevator's frame, okay, initial velocity of the bolt is 0, okay, and displacement of the bolt is equal to 6 meters downwards at t equal to t. So 6 should be equal to half 12 into t square. So this is the motion of the bolt in the elevator's frame. Now this can incidentally also be justified by Newton's laws application. Free body diagram method. If you're in the frame of the elevator, non-inertial frame, going up with an acceleration of AE, then the bolt experiences its own weight. It also experiences pseudo force. Therefore, in this frame, it has an acceleration That's one more way to understand the relative acceleration.
Sir, I am having doubt in the second one.
Yeah.
So how can we say the displacement is 6 meter because the lift is also moving with
No,
respect
but
to
that is the
time.
thing. We are seeing it from the reference frame of the lift. No? We are inside the lift. So in our frame, is the lift moving? No, no.
Okay.
So that is the advantage now of doing it in this reference frame, because in this reference frame, the lift's floor becomes stationary for us. No?
Okay, sir.
Okay. Now, if you look at the motion of the bolt in the ground frame, so an observer on the ground, what he sees is that the elevator is, let's say, here with the bolt just about coming loose at time t equal to 0. Both of them have an initial velocity of 0. Okay. But the elevator has an acceleration, okay, and the bolt has an acceleration of g downwards. So after some time, let's say the elevator has reached here, and by then the bolt has reached here. So this is the displacement of the bolt in the ground frame, and this is the displacement of the elevator, the ground frame, and their sum should be equal to h, 6 meters. You can see that in the ground frame, the displacement of the bolt is half gt squared downwards, and the displacement of the elevator, so at t equal to capital T, the sum of their magnitudes should be equal to h. Same thing, t is 1 second. This is obvious because that we already calculated. But now substituting this here, we can see that the displacement of the bolt is 5 meter downwards, and the displacement of the elevator is 1 meter upwards. So this becomes the answer. Okay, so these are examples of relative acceleration. Okay. So these are basically the concepts of relative motion. Now we'll see more application examples. Now let's see another interesting type of example to do with relative acceleration. So we have a situation like this. This is a height of 80 meters. Okay, now from here, okay, and a ball A is released from rest at t equal to 0. So it will fall vertically like this. But simultaneously at t equal to 0 from the ground level, another ball B is projected vertically. With initial velocity (40 meters per second). Take G as 10 meters per second square. So find the time and position at which A and B cross each other. Now you can do this by the normal method also without involving relative motion. But this will be a very interesting situation if we solve it by the relative motion method. So we'll discuss about that. Just try working this out using relative motion. Yes, very good. The answer is correct, Siddharth. Okay. Now see, one very interesting thing we can do in a problem like this is taking the common reference frame like this. Okay, we can see that initial velocity of A is equal to initial velocity of B is equal to 0. So if you look at the motion of, for example, B relative to A, sorry, initial velocity of B is not 0. Initial velocity of B is plus 40 j cap. So if we look at the initial velocity of B with respect to A, it is plus 40 j cap in meters per second. Acceleration of A is minus g j cap. Acceleration of B is also minus g j cap. So relative acceleration of B with
1 will
respect,
be plus j cap, no?
no, it is not, beta. You cannot take two different axes for two different objects within the same problem, right? You have to follow the common axis. You got my point? This is why I have drawn the system of axes here, no? Y-axis is upwards. If I'm considering relative motion, then I cannot take a different axis system for A and a different axis system for B. I have to take the common system of axis for both. So this becomes 0. So now this gives us a very interesting result that the motion of B relative to A is a uniform 1D motion. Okay. So the displacement of B relative to A will be this uniform velocity into time. So suppose if they collide at time capital T, then the displacement of B relative to A should be 40 T j cap. And you will see that this should become equal to 80 j cap. Because B was 80 meters below A. So by the time it comes and hits A, with respect to A, if you're sitting on that object A, what does the displacement of B look like? It looks like 80 meters up towards you. So this time should be how much? It should be 2 seconds. And once you understood this, now you can understand that the position where they collide with each other. So for that, you look in the ground frame. You'll see that A started from here at t equal to 0. So in t equal to 2 seconds, A makes a displacement of how much? Displacement of magnitude half gt square. So this will be 20 meters in time 2 seconds. Okay. Whereas B started from here at t equal to 0 with 40 meters per second. So in a matter of the magnitude of B's displacement will become 60 meters. You can see that this is the position at which they collide. But once again, you can see that with proper sign convention, if you write the displacement, A's displacement is minus 20 or and B's displacement is plus 60. So the displacement of B with respect to A is 80 J cap by the time they collide. Okay, so hope this example is also clear to all of you. Okay, people, so hope this is clear. Now, moving on to another interesting situation in relative motion. Relative motion of a swimmer or a motorboat moving in flowing water. Okay, so for example, suppose we have a situation like this, that there is a section of a river which is almost a straight line, and in this the water is flowing at a uniform velocity. So it's a pretty rapid river, so water flows at constant velocity like this. Now there is a motorboat which moves at 18 kilometers per hour with respect to still water. That is, if the motorboat was moving in a pond where the water is still, then its velocity with respect to that still water would be 18 kilometers per hour. Okay. So now this motorboat goes from this position downstream till it reaches somewhere here at a time of 20 minutes. Okay. And then it makes a U-turn and comes back upstream. Let's say the point P, the point Q. So starts from P at t equal to 0, moving downstream for 20 minutes. And then turns 180 degrees to move upstream back to, we want to find the velocity of the motorboat as seen from the ground frame when moving downstream, that is P to Q, and then when coming back upstream. And secondly, the total time of the trip. Neglect the time to take the U-turn. Okay, so let's understand how we will apply the concept of relative motion over here. So of course, here we'll apply relative velocity concept. There is no acceleration involved. Okay, so here the concept we'll be applying is that the velocity of the boat relative to water has magnitude of 18 kilometers per hour. This statement here implies this. So it's a question where relative velocity is, yes, very good, Siddharth, that's correct. So relative velocity is given and absolute velocity has to be calculated. Okay. So we'll use this concept that velocity of the boat with respect to the water is velocity of the boat minus velocity of the water. Okay. This is in ground frame. So in this case, now this is the unknown quantity, this is known and this is known. So we will reverse this equation and we'll say the velocity of the boat in ground frame is the velocity of the boat relative to the water plus the velocity of the water. This is what we'll apply over here. So for the downstream journey, we take this as our x-axis. The velocity of the boat with respect to the water is plus 18 I cap, and the velocity of the water is plus 9 I cap. The net velocity of the boat in the ground frame will become plus 27 I cap. So the boat will go at 27 kilometers per hour downstream with respect to the ground frame. Okay. But when it comes to the upstream part of the journey, you can see it becomes different. Okay. Again, taking this as a reference, if we do, then the velocity of the boat with respect to the water this time is minus 18 I cap. In the water's frame, the boat is coming upstream at 18, but the water continues to flow downstream at 9. So the velocity of the boat in the ground frame will become minus of 9 I cap. So we can say that the velocity of the boat will be 9 kilometers per hour upstream with respect to ground. Okay. So when the boat is going downstream, an observer on the ground, he will observe the boat to be moving at 27 kilometers per hour. And same thing when the boat is coming upstream, after taking the U-turn, he will observe it to be moving at 9 kilometers per hour. Yes, very good, Akshat, Siddharth. So now the total time of the journey downstream time plus the upstream time. Now T1 is given to us to be how much now? 20 minutes, right? So T1 is 20 minutes, that is 1/3 of an hour. So therefore, PQ distance is how much? It is 27 into 1/3 or 9 kilometers. Therefore, T2 will be that same distance of 9 kilometers, but divided by 9 kilometers per hour. Okay, this is the upstream situation. So the downstream situation. So that's 1 hour. So the total time four by 3 hours or 80 minutes will be the total time taken.
Sir, done.
Okay, done. Understood this now. Now let's see the two-dimensional situation where this kind of thing is happening. So once again, we have a river which has a straight horizontal section. This is the top view of a river, and the water is flowing at a uniform velocity. Now this time we have a swimmer who's trying to swim across the river, but the velocity of the river current will tend to make him drift downstream. So same kind of situation, but the river water velocity is given to us this time as, let us say, 3 kilometers per hour. This is the river current velocity. Water flow. Okay. Now a swimmer orients his swimming like this. Okay. But because of the drift of the river, he ends up moving like this. So his body is oriented like this, but the river will make him drift and he'll end up reaching here. So if he starts from here at t equal to 0 and he reaches here, also the width of the river is given to us. Okay. So a swimmer S swims at 4 kilometers per hour relative to still water. In stationary water, his swimming speed is so much. Okay. And he swims perpendicular to the river current. As shown in the diagram. So first of all, find the swimmer's velocity with respect to ground frame. And find the time taken across the river and find the amount by which he has drifted downstream. If this distance here is x, then find the distance x by which he has drifted downstream. Okay, so we'll be using the same concept in this question, that the net velocity of the swimmer in the ground frame is the velocity of the swimmer with respect to water plus the velocity of the water. Okay, so this is the net or absolute velocity of the swimmer in the ground frame, whereas this is the velocity with respect to water, the velocity in still water, that's, and this is the river current velocity. Okay, but only now we'll have to apply it in a two-dimensional situation. So you can draw a system of axes and make use of I cap j cap component method. Okay, or you can go with a geometrical picture, triangle law, kind of draw a vector triangle. Both are equally convenient in this particular case. Okay. Yes, very good, Soham, that's correct.
What is the distance?
Oh yeah, that width of the river has to be given also. So the width of the river, let us say, is half a kilometer. So it's 500 meters. Yes. Yes, Siddharth, good, your answer is correct also. Take the width of the river given as 500 meters. Yes, Akshat, correct. Yes, very good. The other answers are also correct, people. 1/8 of an hour or 7.5 minutes, whatever. So what we'll see here is that when we draw the vector diagram, the velocity of the swimmer with respect to water, that is a vector like this. Okay. And that is of magnitude 4 kilometers per hour. Whereas the water itself is flowing at 3 kilometers per hour. This is the velocity of the water. So the net velocity of the swimmer will become the vector sum of these two. It should be like along the diagonal of this rectangle. So the velocity of the swimmer in the ground frame. So this will become 5 kilometers per hour. And this angle will become 53 degrees. You can also write it like this. If you take this as the X and Y axis, you can see that the velocity of the water in the ground frame, the velocity of the swimmer with respect to water, so what then happens is that the swimmer ends up moving along a path which is like this at 53 degrees. If he drifts by distance x, when he reaches here at time capital T, the displacement should be equal to the velocity into time. So the displacement, as you can see, is x I cap plus t j cap, and that should be equal to 3 I cap plus 4 j cap into time. So x should be 3t, and this distance d should be 4t. So the distance is 0.5 kilometers. So the time taken is 1/8 of an hour or 7.5 minutes. And therefore, x is 3 into Okay, people. So with this, we will conclude today's session. Okay. We will continue with more problems of relative motion in the next lecture to wind up this kinematics section. And the next chapter after we do kinematics, the next chapter we'll pick up will be circular motion. So even circular motion, the first part is about the equations of motion. So it's basically kinematics only, but for the specific situation of an object in a circular path. So that's it for today's session, people. Wish you all the best. Have a nice day. Make sure to revise this session carefully.
Yes, sir. Thank you.
Sir, sir.